Okay, now, personal experiences with cable-stayed bridges may be just interesting for you. I've worked 40 years as a bridge engineer all over the world, and of course I've done many other non-cable-stayed bridges, but it so happened that I gravitated to that. And I just want to tell you some examples there, so not so scientific the last lecture. At the end of my study, at the end of school, I had the idea I wanted to be a bridge engineer with big bridges all over the world, and consequently the most famous bridge engineer at that time was Professor Fritz Leonhard. I went from Hamburg, my hometown, to Stuttgart to study under Leonhard, which I did, and at the end I went to him and asked him whether he could get me a job abroad, because he always pointed young engineers should go out. And at that time, 1970, 1969, it wasn't so common. Anyway, he got me a job in South Africa with a contractor there, Grenegger, who used the post-tendering system, and I went down and was a year in Johannesburg in the design office, designing everything from buildings and industrial plants and some small simple span bridges. And then after a year, was said, okay, I wanted to go on site, or should go on site. And then they came up and said, we have some nice, beautiful in Botswana, black state north of South Africa. And what was done there was a copper nickel mine was installed, and our Grenegger and Richard Costain joint venture built all the structures above ground, from rock coming out to 95% in flotation, and with breakers and all sorts of things, large foundations, and it was interesting. So I went there for a year. We were 4 people running the site, 3 from England and myself, and that's how we started. First time I came up with my Volkswagen from Joburg. We started in tents. I was wearing there the usual habit, what we call a safari suit. In South Africa, I think it's still used today. So I was 25 at that time. Haven't changed a lot, I know, yes. And so after that year I came back and started with Leonhard's office in Stuttgart, first on some German bridges. I've shown you the cable-stayed alternate there. I did by hand the load configurations for stress influence lines by hand. Kernpunktmomente, I told you all about it, since I did that for 2 or 3 weeks. I never forget it. So I worked on this one early on. Later I did most of the checking for Professor Leonhard, who was checking engineer for the actual Kocher Valley Bridge, this one, when we could place the piers in the slope. Then came Neckar Valley, I told you, with the underslung side spans, and here we were not too happy when Leonhard came up with doing a single part, because we had the tender design ready, and so we had to redo the thing, but he said, no, that's important, it's a beautiful valley, we must open it up. Okay, great man. Then came Fleje. We did the detailed design for this part, and I became project engineer here. Very interesting. That was built span-wise with a 60-meter spans with a self-launching truss. We see here the tower is half up, and some of the engineers which are still busy, and I have contact, it so happened, was, for example, the steel part was, well, you probably don't know, Professor Weyer, Dortmund, with whom I'm, and Professor Albrecht in Munich, where my son did his diploma thesis. They worked on the steel part. I worked on the concrete part. It's all early 70s, long time ago, but one keeps in contact. That was it then, because then I had to go to the US for PESCO, and only after the reunification, so the next 20 years I only did bridges abroad. I did bridges in Germany. This is the A4 to Dresden, and the old bridge had to be taken off, keeping the old piers. And so what we did the new one on auxiliary piers on the side, had the traffic running here, then taking the traffic over here, removing that and shifting transversely the whole, 600-meter long bridge over. Quite interesting. Warnow Bridge, A20 at the Baltic Sea, Ostsee, Baltic Sea near Rostock. I went for that because after 30 years or so in Stuttgart, I wanted to speak my local North German dialect again, Plattdeutsch. And so we gave in a very low offer, and we got the job. It's a 70-meter span. But I went to all the meetings myself and found some people, so I could speak my dialect again after 30 years in Stuttgart. Finally, I was quite a bit in charge, although I was managing director, but sometimes I tried to do a little bridge work. Still, if you come from Dresden into Berlin, the A13 becomes A113, and then you come to the Neuköllner Dreieck, the New Cologne triangle here. Let me look at it. You come, das ist der Norden. You come from here. Come from here, Grenzallee, and then you go on to Tempelhof. And that's 4 levels, -1, ground level, +1, +2. And it's completely no crossing over. And so this is what we used to call in the United States a spaghetti intersection. Not so usual in Germany, but it was quite interesting. And next to it then is this arch bridge, where we said we don't want 2 arch bridges side by side, meaning 2 arches near one another in the center, but we combined the central one into one. So these 3 have similar dimensions, although roughly speaking these have double plate sizes, continuous roadway slab. So we think that was done from aesthetic reasons, and I think it looks much better than the usual 2 arches side by side, combining them. Well, cable-stayed bridges, as I said, when I was doing Fleer, I had before 1973 started PESCO Kennewick, but dragged on, and we had a design so far, and this small American office was supposed to do the rest. And I was told, well, I'll go there and check and see. In March 76. And when I came there, I saw there was nothing there. What was there you could just throw away. No good. And they had started on site. So I looked at it and then said, okay, I phoned Leonhard and said, listen, I've got to remain here, otherwise we run into trouble. Then there is construction ready and there's no construction engineering. And so he got it organized, and I phoned my wife and said, listen, you better come over here. Our son was 6 weeks old at that time. And so she came, and I had rented a house completely. People were gone away for a year, and borrowed from the office all the children's equipment, bottle warmers and things like that. So my wife came with a suitcase and a kid, and we lived there for nearly a year near Seattle, in Olympia, Washington. It's across the Columbia River, and it was very demanding, and it was the first time that I did it myself. And we had to do a lot by hand. Strudel program didn't have the capacity. Anyway, after I was through with that, I thought, well, if you've done it, nothing, you shouldn't be afraid of anything else, because the construction went through exactly the way we had designed it. And I told you this little point of honor. At the end, the cables had not to be restressed. They were as they should be. So we had an excellent contractor who did it the first time, Peter Kiewitz Sons, Martin Kelly. And I did it the first time, but it came together. And after that, when you've done once, I was completely alone, of course. Leonhard had sent me alone. I had nobody there. There was no email or fax, or these things were not in existence. We had 9 hours time difference, so we didn't telephone so much. We wrote letters by mail. So I was on my own, and that helped a lot. They threw me and I swam. Thank God, I kept my head above water. But after I had done that, not much I wasn't afraid of much. We used precast elements because the contractors didn't want to do free cantilevering cast in place, match casting, epoxy joints. I've told you all that, quite new, and it worked beautifully. Then came East Huntington, also like Pesco, a world record for one side, for one tower only. There, the two piers were there. We used precast elements. Came Sunshine Skyway. Now we are already in 81. 15 years I nearly designed only cable stayed bridge in the US. There were no cable stayed bridges. We did the first ones. And all the first ones first we designed them, and then we were in competition, and those we won. So until 93, end of 80s, I was mainly designing in the US. Tampa Bay we didn't get. Here we had both alternates, steel and concrete, so small wonder one of our alternates was built, the composite across the Mississippi. And then I told you about the ship collision. We had to do something for a bridge, one of our bridges in South America, and protection against ship collision. And I looked into that and found there is nothing in existence, not in code nor anything else, to determine the, say, equivalent force, the impact force of a ship running into a rigid pier. And to design something, you had to know the forces. So I looked into it and found out that in my hometown, there were collision tests done for the nuclear-powered ship Otto Hahn. At that time, there were trade vessels supposed to run with nuclear power. It's not been done. And so for the protection of these nuclear reactors in that ship, there were tests run, and you see here, you see the size of a man, size of a ship. These were sizable tests with all sorts of things. And I got to know the engineer who ran it, and because I didn't understand anything of that, I looked at it with a fresh view and made some sketches and found out, which strange enough nobody else had found before, that the impact force is proportional with the square root of the ship size. Very simple, and some factor here. And so this formula then has been used now all over the world for determining impact force depending on the size of ship. And I used plus minus 50%, which is true because it depends very much on the construction of the ship's bow. If you have a soft, not underbelly, but a soft, say an oil tanker is rather soft. If you have a cruise ship, it's in the middle, and if you have a warship, it's very strong. And so ferries are in between. It's better to use this as general and that, say, plus minus 50%, depending on the bow structure of the size of the ship. Well, that was, of course, too difficult then, and now it's been used with a 75 fractile, then it's not 0.88, but it's 0.98 and things like that. But this formula, I found at that time, is now used worldwide. And, Sunshine Skyway, I showed you our design, which lost. This was the finally used design by Jean Muller. The bridge had to be built newly because the old bridge was hit by a ship in a rain situation and fell down, 30 people dead. So the new bridge, of course, that had to be protected against ship impact by, as we used to say, by belt and suspenders. And what came out was the main towers were on one hand then protected by an artificial island, I told you all about it, plus these dolphins, and the side piers were all deeply protected by side piers. But that was the outcome of this little study on ship collision. Then came Houston Ship Channel crossing. Just thinking. Oops. The Houston Ship Channel crossing, there was a tunnel which was too small. And you see here, that's Houston, Texas, oil producing area, right in the middle where all the oil is processed. On one hand, it's non-US oil comes in from the Gulf of Mexico through the Houston Ship Channel into the refineries here. And so there's a lot of petrol trucks going up and going over there. And a lot of space required, and we looked into it and found, okay, we'd rather make two separate beams. I told you about it, separate towers. It's a hurricane area. I went through a hurricane there. I went through 3 hurricanes in Tampa, Florida. Really where we were supposed to be evacuated, but I didn't. We had a first floor there. I said, well, if we are flooded, before I get wet feet, I sit in the first floor. I never went on the road, but we were 3 times asked to evacuate, so I know about hurricanes. And here we had, it was for the construction, the governing design, the governing load, hurricane, which is 210 kilometers per hour, 230. Not quite as much. Helgeland was 270, was more. But 230 is quite something. And so we did free cantilevering to both sides, and for a hurricane, it wouldn't have been stable. So we tied down, I'm not sure you can see it. Yeah, you can. There are tie downs, temporary until closure, against hurricane, and a hurricane, a heavy one, went smack across the site before center span closure, and the bridge behaved as decided, was measured, 1.7 meters plus minus up and down, the tip, but everything is considered. So it worked very well. I told you already about the coloring we took into account, so I don't have to go into that much more. In Columbus, Ohio, there are the Scioto River runs really through downtown. It's partly developed, And there are three I call major true arch bridges, series of arches underneath. And one of it was obsolete and had to be replaced. And we got the job together with a local Burgess and Nipel company. And there was a concerned citizen committee, as is everywhere now in the US, and there were workshops where all the good citizens of Columbus, Ohio could come in and tell what they wanted. In the beginning, what's now being found out in Stuttgart as public involvement, beautiful, we did already 15 years or 20 years, 20 years ago in the US. And they said, no, we wanted a slender bridge. They said, no way, we don't want a highway bridge, we want an inner city arch bridge. Yes, but a true arch, they couldn't pay, as there was, you know. So Leonhard finally came up and said, okay, we do what we call a plate arch. These are actually just plates, deep haunched girders, 1 foot thick, 30 centimeters, with a haunch. If you look here underneath, there's no arch in between. But they look good enough as an arch, and they were payable. And so that's how this, I think, very nice, we had good architect, what was his name? From H2L2 architects, former or original a Pole from Poland, Tom Piotrowski. He was the architect there. He's now head of H2L2. So I think we made a nice bridge together with the concerned citizens of Columbus, Ohio. Then came the big competition, Annapolis Bridge, I told you about, where I think we won because we respected the history of the Onassis Academy. And then came what I personally call the most daring bridge I've ever done. I told you all about it. 425 meters, 1.2 meters deep. West coast of Norway at the polar circle with real heavy storms. This is here a picture at the early in the beginning, and that is, in German it's called Gischt. The water drops being pushed up by storms 250 kilometers plus. But it worked. It still stands beautifully, and of course the most critical part is just before center joint closure, where we had here 210 meter free cantilevers. And every winter, or from fall to spring, 2/3 of a year, there are these heavy storms. And I'm not sure, knowing what I know today, whether I would have dared these skinny dimensions we did at that time. But Dr. Kovacs did all the aerodynamics and said, it works. And I believed him. You can't do more with this voodoo voodoo dynamics these people do. You can't, as a regular engineer, you can't really understand and check. You have to believe somebody. But we've worked so long together, and he was right. It worked. But I'm not sure I would do the same again today. Of course, there was also beautiful weather, and free cantilevering then to both sides, cast in place where we had the final cable supporting the traveller. I told you all about it. Then, now here we go. Scotland, here we come. Leven River Bridge at a new town north of Edinburgh. We did with an architect, completely built on scaffolding, no post-tensioning, taking into account cracked section under service life load and load redistribution then for the cracked concrete section. Normally we have post-tension, then there's not much cracking. But here it was only reinforced, so we had a lot of cracking, a lot of redistribution of moments. That was a special thing here. Well, in addition to designing, one can't avoid checking. It's not a real interesting job. I'd rather design a structure than check it, but sometimes one has to do it. And I could not become a checking engineer in Germany because for that you have to show 10 buildings. And I was never considered clever enough to do buildings. I was restricted to bridges, so I could not become a German checking engineer. So I did all my checking abroad. And for that you need a registration as engineer there. For example, I started PE, professional engineer in the US, which is, after getting your degree, accepted and all that. It's 2 written examinations each hour, 8 hours each. And I did that back to back, Thursday and Friday. And after I passed, my colleagues in America said, well, maybe he isn't as stupid as we thought, because the PE exam in this way, back to back, is not normally done in the US. You have some years between. Canada, I had to do an additional on Canadian law, which is basically British law. The House of Lords is still the highest appeal in Canada and things like that. In the UK, I had 1 hour verbal, 1 hour written. And after you've become a chartered engineer, you can then become members by the civils and by the structurals. China and Australia and Malaysia, they then believed me, and I didn't have to take exams for that. So in all these countries I've checked, I've designed. You must have that in order to be able to sign a drawing, and to be a checking engineer where you also have to sign. Roosevelt Lake Bridge in Arizona, right in the middle of a desert. We did a major bridge because that's a dam, ein Staudamm, there in Arizona. An arch was done and we were checking, and the engineers had never done that, the contractor has never done that. So our checking was more to tell them how to do it. But anyway, it worked out quite nicely. And you see, it's a 310 meter span, something like that, and tied back free cantilever. It was an interesting thing. Norway, Svinesund, across Norway and Sweden, we had a design for an arch bridge, but we didn't win. Bilfinger's design won, Bilfinger and Berger, and they had to bring there, that's a checking engineer, they have to bring check drawings. So they have to pay the checking engineer, but he has to be accepted by the state. And since I had worked in Norway and Sweden, and from my name, Holger Sigurd Svensson, I was considered an honorable Scandinavian. That's 150 years ago that my great-grandfather came from Sweden to Germany. And so I became then, with this and other bridges in Sweden, checking engineer. And it was very interesting because it was a tricky job, slender arch and 2 independent box girders, and the torsional stiffness of the whole structure came from the torsional stiffness of the 2 beams. Was interesting. 1210 meter suspension bridge, Höga Kusten in Sweden, used to be the 3rd longest, now it's probably the 10th, I don't know. I was checking engineer, Coe did the design, Kjessel and Mannerströle together. Was very interesting. It was the only suspension bridge I worked on, and if you just have to check whether it stands up, I mean, it's not as designed. I wouldn't take on the design for a suspension bridge, I've never done one. But to check it, that it stands up, was interesting. Then came Yangpu checking, World Bank gave, or was supposed to give, $100 million loan to China to build the Yangpu Bridge in Shanghai, 602-meter main span, world record at that time. And the World Bank said, that's okay, but we want to check it. So they had 3 checking engineers. Walt Podolny, chief bridge engineer from Federal Highway Administration in the US. We knew one another well, plus the Japanese. We checked all that, and it was very nice. And at the end, I had to give a TV interview after the contract was signed. They asked me about the impression. I said it was very well done. We had very little to criticize. However, I say that with a laughing and a crying eye. Laughing because as a check engineer you are more happy if you can sign it off than if you have to say no good, do it again. Crying because I saw no jobs for my company, Leonhard Andra and Partner. They can do it themselves. And that's what it was. We've never had a major job in China. Sweden, Uddevalla, we had a design with Skanska, I think, but weren't successful, if I remember correctly. But I got the checking, so we worked on the checking of Uddevalla. That's also along the coast between Malmö up to Oslo E60. Ume 11, another cable stayed bridge where I was checking engineer. Interesting was the Penang Bridge in Malaysia. Penang is a major island in the north of Malaysia, where it then goes into Thailand, and it's since many years a holiday resort. And so to develop that in the 70s, I think, the Penang Bridge was built, and we checked it for new loads, and finally it came out okay. Reinforce it somehow, but otherwise it was okay. Golden Ears Bridge in Vancouver, Bilfinger design, where I was checking engineer. Last year, I think it was opened. Interesting because it's a difficult earthquake situation. You can imagine going up California, up into British Columbia. It's not the San Andreas Fault all the way, but it's highly earthquake prone. And the solution here, which you may recall, hopefully, from Rion Antirion, was that between the soil, I say, and the foundation is about something like two layers of aggregate, which in earthquake permits plastic sliding. That was also used here, and we had long discussions due to the time difference around midnight, and of course telephone conferences with people in the US, in Canada, checking my geological specialist and so on. But we accepted it, and hopefully it works. I've worked, and then we'll stop, in the US. In the 15 years I have worked mainly in the United States for Leonhard. I was, of course, then in code commissions. We did the first code for parallel strand and parallel wire cables within the Post-Tensioning Institute, which is now part of AASHTO. We did the first guide specification for vessel collision design. I had worked on that, so I was in the AASHTO committees. And we did the first segmental concrete precast elements, but actually it wasn't that. The main point was the first box girder code conditions, because there was nothing in the US. You use the single span AASHTO girders, and that's it. So these were important new codes which were incorporated into the AASHTO. And I think that will give you a rough idea that I had all sorts of interesting jobs to do, and I've stuck 40 years to what I've, at the end of my school days, said I want to design major bridges all over the world. And I'm very thankful for that I had this opportunity, and I wish you, this is the last lecture we have together, that whatever you want to do, whether bridges or buildings or it doesn't matter what, that you find an opportunity and that you like it as you hope to do now, and that you stick to it. I wish you all the best.